questions. So I guess we can start and then people will come. So it's a pleasure to have with us once more Carolina. This is the second lecture from her mini course. We will have other two lectures, not next week, but the following week, starting the 18th, the third lecture, and the following week, the fourth. So please, Carolina, the floor is yours.
Okay, so thank you, Stefanella. So last time we spoke about Hamiltonian dynamics and perturbation theory, and I know it was a bit too abstract and a bit too vague, but today I wanted to go to the resonance, what a resonance is, and why we spoke about what we spoke last time. So let's begin with the concept of the resonance. So informally speaking, we can say that a resonance occurs when two or more fundamental frequencies of the physical problem that we're studying are in a simple integer ratio, or they are in commensurability. So depending on the different types of the different types of involved frequencies, we will get different types of resonances. We can have mean motion resonances that are when the frequencies of the involved bodies are the mean motions. If we are speaking of a planetary system, they would be the mean motion of the planets around the star. We can have spin orbit resonances where the involved frequencies are the spin angular speed of the rotating planet and the mean motion of the planet. These are orbital resonances, but we can also have secular resonances, which are long-term interactions that gradually affect the frequencies over time. So, for example, we can have the two frequencies involved can be the precessions of the node, the precessions and the absence of the node, or we can have Bonsai-Pavlidov-Kozai resonances in which there is a cyclic exchange between the eccentricity and the inclination of the orbiting body. And there are many others, but I will focus on the mean motion resonances, which are as I said, when the involved frequencies are the mean motions of the planets. And so basically what this means is that if we have two planets, and in this case there is a 2-to-1 resonance described, what we see is that at some point the two planets are in the same configuration, and then the first planet complete two orbits at the same time as the outer planet completes one. And so they are aligned in one position of the orbit, and they are anti-aligned in the opposite configuration. And why do we care about the resonances? Well, basically because there are the number of bodies in some kind of resonance is remarkably large. For example, in the solar system, we have Mercury in a 3-to-2 spin orbit resonance, meaning that every two orbits of Mercury around the Sun, Mercury completes three orbits, three rotations around its own axis. And something similar is observed. We have three mean motion resonances between, for example, Neptune and Pluto, that they are in a 3-to-2 commensurability. And we have more complex resonances, for example, between the satellites of Jupiter, Io, Europa, and Ganymede are in a 1-3-2 mean motion resonance. This means that the two they are in pairwise in mean motion resonance, and this makes the interaction more complicated. For example, the Moon is in a 1-to-1 spin orbit resonance, so it completes one orbit at exactly the same time it rotates on itself. And this shapes the architecture of a system. For example, as we said last time, we have gaps in the asteroid belt. So here there is a nice drawing showing the Kirkwood gaps. So we have gaps in the position of the resonance with Jupiter and with other planets, and so there are some positions in which there is no material in the orbits, and something similar is observed in the rings of Saturn, that they are called Cassini gaps or Cassini divisions, where there are resonances with Saturn. And in the exoplanetary population, we also observe mean motion resonances between the planets. So, for example, here I show you the distribution of the period ratio of the planet. The periods are an equivalent quantity than the mean motions of the planets. And so if we have more than 2 planets in the system, we can plot the period ratio of the system. And here in dashed lines, you see the exact commensurabilities, some of them. And we can see that there are some accumulations opposite as the gaps that we see in the asteroid belt, but we see that there is an action of the resonance in the exoplanets. But we also see that there are many systems that are not in resonance. But what we will do is to try to understand the systems that are near these configurations, or the asteroids that are cleaned via resonances from these gaps. And so there are some possible explanations for how to explain how the systems got in these configurations. And the most likely explanation is that there are slow changes in the frequencies of the system that makes the drift that make the frequencies drift through the resonance. And if the drift is slow enough and the resonance is strong enough, then the system can get trapped in resonance. And in fact, it will remain in resonance and as long as the system continues to evolve. And this is related to the formation of the planets and the long-term evolution of the system. And in particular, it's related to a process called planetary migration. And for that, we need to understand how the planets form. So we know that the planets are formed during the formation of the star. So we will have a cloud of gas and dust, and we have a clump in the middle. And since when it begins to grow, gravitationally dominates, and so it spins and it forms a disk. And so in this disk, we would have other smaller clamps that will begin to dominate gravitationally, and there the planets will form, interacting with this disk, and at some point the disk will dissipate, the gaseous part of the disk will dissipate, and we will end up with a planetary system as we observe nowadays. Of course, this is a nice fairy tale. With a bit more specifics, we can say that the planets are formed in a circumstellar disk or a protoplanetary disk formed of gas and dust. And the fact that there is a planet in this gas modifies the distribution of gas in its surroundings. And so there is a gravitational interaction between the disk and the planet, and so this generates a torque that will modify the orbit of the planet, and the direction and the speed of the migration will depend basically on the local properties of the gas and the mass of the planet. And so different types of planets are affected by different processes. And so small mass planets are affected by what we call type 1 migration. So they are immersed in the disk and they have a lot of material to interact with, while bigger planets, they are affected by the type 2 migration. And these are planets that are massive enough that they carve a gap in the disk. And so they eat all the material in this zone and they have less gas to interact with. And so the migration in this regime is much slower than the migration in the type 1 regime. And in between, we have intermediate migration regimes. And so let's go to the pendulum. And finally, at the end of the day, I will try to do a relation of why we go from the migration and the formation of a planet to this very theoretical stuff. So I know that speaking about the pendulum sounds a bit unrelated to everything, but the pendulum describes the fundamental model of the resonant motion. And as the harmonic oscillator is for linear system, the pendulum is the paradigm of nonlinear system. And so if we have a mass oscillating at a fixed distance L, we can construct the Lagrangian of the system, where we have the kinetic energy minus the potential energy, and recall that the Hamiltonian is the sum of these two quantities, so we can construct the Hamiltonian from the Lagrangian, and we will get an expression like this, where P would be the action and theta would be the angle in the action angle variables, and we have this that would be the perturbation parameter. And so depending on the energy of the system, we would have three different regimes of the motion of a particle. So if the energy is small enough, we will have libration or oscillations. So we would be inside the blue curve, and so the angles will not take all the possible values, but the angle would be restricted. If the energy is big enough, we will have that the angle can take all the values between 0 and 2 pi, and we have a rotation. And in between these two regimes, we have a separatrix. So the energy of the system is exactly the Hamiltonian. And so if we are so if the variation in the angle is very small, we can do an approximation and we can get this expression right here. So for this Hamiltonian, we can find the fixed points using the Hamiltonian equations. That remember that the Hamiltonian equation is the derivative of the Hamiltonian with respect to the two variables, and so we have that a fixed point in P equals 0 and theta equal to an integer multiplied by pi. And we can assess the stability of the fixed points by using the second derivatives. And we see that the point 0, 0 is a stable fixed point, so it's an elliptical point, while the 0 pi or 0 minus pi is an hyperbolic fixed point, so this is an unstable point. And we can, in fact, compute the width of the libration region. And so this region is defined as the difference between the largest and the smallest momentum in the librating orbits for a fixed value of the angle, which in this case is theta equals 0. Um, and in that case, we can compute the value of the Hamiltonian so we get the value of the separatrix, and we can get the critical value of the action that give us for this energy, and we get that the width of the libration region is twice the value of the critical action. And so all this information combined give us the typical cat-eye phase space. So where we have in the action angle variables, in the action angle phase space, we have the libration. So when the orbit is bounded and it cannot it cannot take all the values of the angles. We have rotations where the angle can take every value between 0 and 2 pi, and the action is not restricted to some values. And we have in between, of course, the red dashed line is the separatrix. And so, if we try to understand the mid-motion resonances in the Hamiltonian formalism, and going back to what we said on Tuesday, we have an n degree of freedom Hamiltonian, to which we are able to find a specific solution of the system by computing the generating function. And recall that this is the aperture part of the Hamiltonian, so we know the exact solution for this Hamiltonian, and we have a perturbation to the aperture Hamiltonian. So in order for this generating function to be valid, we need this quantity right here to be different from 0. And if this is different from 0, we can find our generating function that will give us the solution to our Hamiltonian, because it will allow us to find a new Hamiltonian that only depends on new variables, and we will be able to write the Hamiltonian only in terms of the actions, and all the angles will be linear in time. But for a moment, let's imagine that there is a combination of this index J that such that this scalar product is equal to 0. So in this case, the generating function is not valid anymore. So if that's the case, we are in what we call the small divisors problem. And we need to treat the problem different. So let's, for a moment, consider the case in which we have two n equal 2. So in order to for the equations and the notation to be simpler. So the scalar product would be given like this, where in this case we made evident the fact that the frequencies depend on the actions, and so the actions are the initial conditions of the system. And so for these specific initial conditions, we said that we will treat the scalar product as equal to 0. So in order for this to happen, the frequencies will satisfy this condition here, where these two values are integer quantities, and so the ratio between the two frequencies that depend on the initial conditions will give us the location of commensurability. And so this situation right here is known as an accidental degeneracy. and it only occurs for a specific set of initial conditions, the value of J1 star and J2 star, that, as I said, give us the location of the resonance, the K2 over K1 resonance in the space of the momenta. And so why is this a problem? Well, because in the case of exact resonance, so in the case where this is equal to 0, both frequencies are not independent anymore. And so we don't have any more 2 degrees of freedom in the problem, but we only have 1. So the system is over-dimensionalized, and the perturbation theory breaks down. So we cannot treat the problem as we did last time. So what we do in these cases is we have our unperturbed Hamiltonian, and we have the perturbation parameter and the perturbation that, since we asked for the perturbation to be periodic, we can perform a Fourier expansion in the angles, and we get this expression right here. And as we said last time, we can perform a canonical transformation to go from an old set of variables to a new set of variables, such that we can transform our Hamiltonian to only depend on the actions and not on the angles. So we would be able to know this exact solution of the system. So if that happens, we know how the transformation equations between the old and the new set of variables are. We know that they depend on the perturbation parameter, and we know what's the shape of the canonical transformation. That will only be valid if the division here is different to 0. So as long as this is different to 0, we can obtain the exact solution of the system. But since we said that this is not the case, because we are treating with the accidental degeneracy, what we do is to split the Hamiltonian in fact, we split the perturbation function in 2. So we have the original unperturbed Hamiltonian, we have the perturbation parameter epsilon, and we divide the perturbation in order to remove or isolate the problematic terms, that in this case are the periodic terms, that are the ones that give rise to the small divisors problem. And so we have our secular Hamiltonian that has this form here. So all the terms that are different from K1, K2, which are the ones that give us the small divisor. And we have in the resonance part of the Hamiltonian all the terms that give us the problem. So for this new part, the Hamiltonian, the unperturbed Hamiltonian plus the secular part of the perturbation, we can treat it as before, because we know that this is a non-resonant system. And so we know how to solve this with our canonical transformation and everything. And so we have our new Hamiltonian, which has the new unperturbed Hamiltonian with the new actions that give us the exact solution, plus only the resonant part. We have here the resonant terms. So we can perform new canonical transformation, and we can construct our new 1 degree of freedom Hamiltonian, in which since the angle phi2 related to conjugated to I2 is not in the Hamiltonian, we know that I2 is an integral of motion, so our Hamiltonian only depends on I1. And we get a phase space with this shape, which is very similar to what we had before for the pendulum. So now what we have is that the center is displaced from 0, 0, but the same features are observed. So say that the center of this libration region is in I10, so near this value, the system circulates, and far from this value, the system librates, and far from this value, the system circulates, and we can always take a resonant system to something similar to the pendulum. And so we say that near mean-motion resonance, so near the periodic orbits of the unperturbed Hamiltonian, the Hamiltonian that we construct is called diffeomorphic, so, to a pendulum, so meaning that this preserves the main features of the motion. So basically we have circulation, aseparatrix, and oscillation, aseparatrix, and circulation. And so just a final comment on this. This is something that we explain for n equal to 2, but of course this can be generalized to any degrees of freedom. And the solution would be the same. We will isolate the problematic terms and apply the perturbation theory to the rest, and we will get the same features in the motion of the interacting bodies. And so let's imagine now that we have a system with 2 degrees of freedom that has two resonances. In any system of Q-order mean motion resonances, we have Q pairs of fixed points. And so in this case, and so we know how this resonance would look like. And so here in violet, you see the separatrix of the resonance. And so we have one resonance centered in 0J1 and the other in 0J2, and the width of each of these resonances is delta J1 or delta J2. So this is the maximum value for theta equal to 0. And so as long as these resonances are separated enough, we have two isolated resonances that will not interact with each other. And so this right here, the red line, give us the distance from the resonance. But if the width of these two resonances is equal or bigger than the separation between the two centers, we have a condition for a resonance overlap that has some implications in the physical problem. So in this case, when we have that the two separatrix are touching each other, independent, so non-resonant motion is not possible in this region. So of course we can have non-resonant motion with bigger values of the action, but not in this region right here. Any initial condition that is initially trapped in this resonance can eventually reach the separatrix, and through the resonance or through the separatrix travel to the other resonance and get trapped in the other commensurability. So these resonances are not isolated anymore, but they are interacting. And so now the orbits are not restricted only to one center of libration, but they can shift between the two of them. And this is a condition for global chaos. Yeah. And so, as I said before, the pendulum is the fundamental model for the resonance. So it allows us to describe the features of the resonant motion. But it has some, and so we are able to analyze or to analytically estimate the properties of the resonance. But there are some limitations with this model. And so there is the second fundamental model for the resonance, which was described by Henrard and Lemaitre in 1982. And this is a 1 degree of freedom Hamiltonian with actions S and angles sigma, and N is a constant. And so the main difference with the pendulum model is that now we have linear terms in the Hamiltonian. And in this model, we can do exactly the same. We can find the fixed point for the system by solving Hamilton's equation. From this equation right here, we see that the sigma can the fixed points in sigma are 0 and pi. But this equation right here is not so easy to solve, so we need to perform a canonical transformation and go to a new set of variables that lead us to a cubic equation, which is this one right here, with some combinations of the constants, and we need to solve it numerically. And once we have that, we will have the local extrema of the Hamiltonian in the h-axis from this new hk set of variables. And we have that when the discriminant of this equation is bigger than 0, we have 3 different real roots. But when this is negative, we have only one real root, and in the middle, we have the case in which the discriminant is equal to 0, and we have multiple real roots. And this leads us to the case in which we can find the value, the critical value of the action n that give us the value of the separatrix. And so once we have all these values, we can have a new canonical transformation that take us to the eccentricity and semi-major axis plane. And we want this because now these are orbital elements. Now this is a value for the planet and for the asteroid. And so if we understand this, then we are able to understand the resonant motion in something that we can observe, like the orbital elements of the system. So here we see the level curves of the Hamiltonian for different values of n. So we have the phase port rate in this new variable. And we can analyze what happens to the two different fixed points, what happens when sigma is 0 and when sigma is pi. So for sigma equals 0, we are in the top part of the plane, and we have a pericentric branch right here, which is the family of fixed points that are linearly stable. And in the case with low eccentricity, we are far from the nominal value of the resonance, which is marked here in red. And once we approach the resonance, the eccentricity grows exponentially. In the case in which sigma is equal to pi, we have the apocentric branch of the fixed points that are stable or unstable according to the resonance, to the distance of the resonance. And everything changed once we reach the value of the critical value of the separatrix. And so we can go to the plane of these variables that we have here. And if we are in the case of n smaller than the critical value, so in this part here and up to the dash curve, we get that the system can oscillate, or we see librations that are known as kinetic librations, in which there is no resonant motion because the system is circulating in around the center, which is not the origin. So if we increase the value of n, this shape is not a circle anymore, but there is no separatrix because we are in this part of the plot. But if we are in the case with bigger n, we get the separatrix, which is marked here in dashed line, and we have two different regions of circulation. We have the one which is displayed from the origin and the one outside. But we have the part of true librations, dynamical librations, which is the part inside the separatrix. And as long as we keep increasing the value of n, we get bigger and bigger regions for the oscillation. So the oscillations are bigger. And so to summarize, what we got is, so we have the two parts of circulation, which is the red part here, which is the outer circulation, which is what happens outside the separatrix. We have this part, which is called inner circulation, which is the kinematics librations around the not the center, so displayed from the origin. And inside these two crosses that will be the separatrix, but we still need to explain how to compute them, we have the true librations. And so we need, as I said before, we need to construct the separatrix, and for that we need to compute the value of the Hamiltonian for different values of n. And so we can still work in the semi-major axis versus eccentricity plane, and we can compute the hyperbolic fixed point for different n. And we get the values of the separatrix for the inner pericentric branch, because this is related to the inner circulation, and the outer circulation. And now so now we can relate this to what we were speaking at the beginning about the formation and the migration of the planets. So now let's say that we have our Hamiltonian, exactly the same as before, but now we have a quantity that is varying in time. So so if this quantity is varying from the outside, we have what it's called, or what's known as divergent migration. So a particle is approaching the resonance from this side, from the right to the left, and it will always find a separatrix. And so to continue to librate, it will jump to the other side of the separatrix, and it will not get captured in resonance. But if instead this quantity is varying from the other side, so the variation of alpha is bigger than 0, so it comes from the left to the right, we have what is known as convergent migration. And in this case, there is a possibility that we can have capture in resonance, and this capture will depend on the value of the eccentricity. So if a particle has initially low eccentricity, then there is no outer branch of the separatrix in this case, and so it is possible for the system to reach the center of the libration and continue to evolve following the pericentric branch, and the oscillations will be through a constant n, so the motion will be like this, but it will remain captured in the resonance. However, if the eccentricity is big enough, even though the variation of this quantity is convergent, it will reach the separatrix and the capture will not be possible. And so if we analyze this in the plane that I showed you before, eccentricity multiplied by sine of the angle or cosine of the angle, we see that the distance to the origin is the value of the eccentricity, and the radius of this circle is the value of the eccentricity. And so in this case, we can have capture because the eccentricity is not as big as the value of the separatrix. And so the evolution would be from A to E. And so in this case, we are in values in which the n is bigger than the critical value. The eccentricity begins to grow until the particle reaches the critical value of the eccentricity. And the orbit continues to evolve, but inside the libration region. But instead, if we have divergent migration, again, the evolution goes from A to E. Sorry. The evolution goes from A to E. And so, once again, we have an eccentricity that does not reach the value of the separatrix, but we have circulation in the inner, in the kinematic circulation, and this continues until the eccentricity reach the separatrix, and after that the eccentricity is bigger, but it's in the other part of the circulation, so it goes from the outer circulation to the inner circulation, and it can take every value of the eccentricity. And so this was everything that I wanted to discuss today in order to not make it long enough and not begin a new topic, but I'm up for any questions that you want to make.
Thank you very much. It was a great lecture. Very nice also the animation, the resonance animation with the planet.
Thanks.
We need this also in regular classes to make it more, So any questions? Today, I don't know if you know, there is, let me stop recording.